Another feature we did not take into account when building the optimization model is the need for reprocessing some of the amplifiers we assemble. So what we have here is for every task a probability of that amplifier to be reprocessed due to that task not being performed perfectly. So for example, for task 1, 2% of the times on average we'll have to reassemble that or re-perform that task. The same goes for tasks 2. We have a 1% probability of having to re-perform task 3 and so on. So the assumption is the following: if any of the tasks assigned to a station has to be reprocessed, the amplifier entirely has to go back to the beginning of the station, to the input buffer, and has to be reprocessed. And all tasks have to be performed again. So you cannot just do the task which went right, but you have to do all the tasks you have assigned to that station. And the reprocessing follows the same rules in terms of the times for you to do that. So anytime, let's take station 4 where we had assigned tasks 1, 2, 3, 5. So every time we have an amplifier to be assembled or to be submitted to these 4 tasks here, we draw random numbers and get values from this distribution, sum them all, and get the time for the tasks for that station. And we then calculate if we have to reprocess or have to reperform any of the 4 tasks assigned to that station. If one or at least one has to be reprocessed, we send back the amplifier back to the beginning, and we have to get another time, another summation of these 4 distributions, and reprocess it again. And again, once we finished, we check with these probabilities if any of those has to be reperformed, in which case it would go back. It's very unlikely that it happened twice, let alone say 3 times and so on. But if that happened, which is very unlikely, we will have to get a new value for the time and so on. Okay.